Alright guys, so I'm going to continue working on number 1 from LUG. This is going to be the algebraic solution. I'm going to keep it all alphabetical, and it'll end up looking pretty fancy. Anyway, so in order to begin the problem, once you've realized this, once you've gotten to this point, again, I started this in a previous video, so you should check that out before coming here. But anyway, once you're here, you should start making some substitutions. Namely that the centripetal force is defined as the mass times centripetal acceleration. Also, the gravitational force between two objects is equal to the gravitational constant times the mass of object 1 times the mass of object 2 divided by the distance between them squared. Start there. At this point, a logical question is, what are the masses? We're given two masses, so which mass goes where? Centripetal force acts on the thing traveling in a circle. In this case, that's the moon. So the centripetal force acts on the moon, so this left side of the equation should be the mass of the moon. The gravitational force is the force that exists between the Earth and the moon, so one of these masses is the mass of the Earth, one of the masses is the mass of the moon. It doesn't really matter which order you put them in. At this point, hopefully you notice that we have a mass of the moon on both sides of the equation. So in your head, you could consider, okay, if I divided this side by the mass of the moon, it would have basically canceled because anything divided by itself is 1. Then the same thing would happen with this side of the equation. So both of these are going to cancel. Then we will have the centripetal acceleration equals g times the mass of the Earth divided by the distance between the Earth and the moon squared. Notice r does not equal radius, it equals the distance between the center of masses. Centripetal acceleration is further defined as v squared divided by r, so we should use that. The r is the distance between the objects. So it's the distance between the center and the thing traveling the circular path. So it's the distance between the Earth and the moon here. So then you get there. And then, you know, in your heads or on your papers, whatever, you could ask yourself, okay, well I have these two equations, these two symbols, both in the bottoms, both in the denominators. So I should do something about that. So you should multiply both sides by the r. I guess I'll just show this thinking works. So times the distance between the Earth and the moon. This cancels that. We do one side, you do the other. This cancels the exponent. So now I get to the point that v squared, not over anything, just v squared equals g times the mass of the Earth divided by the distance between the Earth and the moon. Note, it's not squared anymore. So I have that equation, and I'm going to pick up with that equation on the next page, because I need a little more space. Okay, so I have this equation. But you know, I'm not asked for any of this stuff. I'm asked to find the period. But the whole point of doing any of this was to get to the speed, which will allow me to make an expression for the period. Speed is 2 pi r divided by t. So I'm going to go ahead and make that substitution now. By the way, this r is the radius of the circular path. It's the distance between the centers of mass, center of masses. Okay, so now my unknown is trapped inside parentheses. It's going to have to be squared. Oh, but then it's in the denominator too. So first of all, let's get rid of this square. And if you wanted to, yeah, I guess you can take the square root of both sides if you really like working with roots. I don't, so I'm going to square it. The square will distribute to everything inside the parentheses, and it'll become 4 pi squared, the distance between the Earth and the moon, squared, divided by the period, squared, is equal to g as the mass of the Earth, divided by the distance between the Earth and the moon. Okay, that's looking kind of intimidating. So now we have two fractions that are separated by an equal sign. A good step will always be to cross multiply. Everybody likes cross multiplying. So let's cross multiply. When you cross multiply those, you find that 4 pi squared, the distance between the Earth and the moon, cubed now, is equal to the gravitational constant as the mass of the Earth times the period of revolution squared. All right, so we get that expression. Got it. So I'm going to grab that equation and I'm going to go to another clean page. tilt, straighten it out a little bit. Okay, so we got there. And we're looking to find the period. So now it's just a matter of isolating your unknown, which is the period. So since period is multiplied by these two, I would start by dividing here. If you wanted to take the square root right away, yeah, I guess you could, but I'll wait for the square root for the very end. So you're going to divide both sides by the quantity, the gravitational constant times the mass of the Earth. This side is going to cancel. So then you get the expression that t squared, I'm just going to write on the left so it looks a little prettier, t squared equals that whole thing. And then to isolate your unknown entirely, all that's left is take the square root of both sides. So the period works out to be this really simple expression. I'm being sarcastic. Not simple. So we get that expression for the period. If you were working on the quiz or a test and you got to that point, you would get 7 out of 8 points on that problem for getting the correct algebraic solution. Then it's just a matter of plugging it in correctly. I would plug in more than I need to, just because I'd be weirded out to plug that in all at once. So I would go 4 pi squared times the distance between the Earth and the Moon, which is 3.82, 10 to the 8th, enter, and then I would say divided by parentheses, 6.67 times 10 to the negative 11th, times the mass of the Earth, which is 5.98 times 10 to the 24th. Do that. And then I would go ahead, take the square root of the answer, and I would find that the answer is like 2.35 times 10 to the 6th, which is not at all the answer on the page. The answer on the page just broke it down from seconds to days, just to keep you on your toes. Also, if you looked it up, you would find that that's the same answer. That 27.2 days is the period of revolution for the Moon around the Earth. To convert from seconds to days, you're kind of on your own for that. Got that. All right, so that was the algebraic solution to question number 1 from LUG. Let's do numerically next.